Okay, so today's agenda, as I mentioned, is a deep dive into 2.5-axis machining. We're going to start out with 2.5-axis explained, then go into machines, a little bit about machines and setup, and then also talk about how toolpaths are actually calculated. So give you a little bit of insight there so you can understand how different machining operations actually work in our product. We'll also talk about cutting tools and the different contact positions and things of that sort with respect to the cutting tools themselves. And then we'll talk about control geometry, also geometry in general, the control geometry as well as the part geometry. And then an area where a lot of people get caught up and confused a little bit is the cut levels. So we're going to be talking about that in depth. And then Don's also going to talk about, give you some basic tips for new users on how to navigate our 2.5-axis machining operations. And so without any further delay, Don, please go ahead.
Hello, everyone. First off, I want to make sure everyone can hear me. If there's any reason anyone can't, just put a note in the chat window and we'll see if we can get that working for you. Okay, 2.5-axis machining. We did go over this a little bit in our last webinar, but we're going to go a little bit deeper in this webinar discussing 2.5-axis machining and how it's calculated and the different types of options that you can use with 2.5-axis. Now, as you can see on this screen, if you look at the part in the top right, the one that with the X and the Y, green Y and red X, how 2.5-axis machining works. The cutter moves in X and Y. It can move in X and Y simultaneously, and it's fixed in the Z. So basically, you start out cutting in X and Y at your first cut level, and then you move X and Y, and when you're done with your first cut level, the tool will travel in Z and then stop at that cut level. So the tool axis, the Z axis, is not moving when the X and the Y are moving. So that's how that's the basic limitation of 2.5-axis machining. The half meaning the Z-axis is there, it can be set to a certain depth, but it's not, the half means it's not moving simultaneously with the other two axes. So the three parts shown under that just gives you an example of a few 2.5-axis operations, facing, and then pocketing and profiling. We're going to be going over those in more detail as we go along. Now let's talk about tools. This slide, if you look at the little red dots on each of the 4 tools, they illustrate the cutting area of the tool, the contact area. And of course, the contact area goes up to the full flute length of the tool, obviously. But with the different tool types, flat mill, ball mill, V mill, and chamfer mill, you're cutting not only at the tip of the tool, but you're also cutting at the full width diameter of the tool. And one thing to note here, we included the ball mill only as a warning, so to speak. Typically, ball mills are not used for 2.5-axis machining. They can be. If you're cutting the bottom of a pocket and you want to have a fillet radius at the bottom, you can use a ball mill, obviously, and that'll leave a fillet at the bottom. But just pay attention that how the ball is going to act when it hits a edge or the edge of a control region. For example, the little graphic there, we call that the waterfall effect. If you look at the tool, it gets to the first few levels at the top of the cut. That ball mill will ride on your control geometry, and it will ride it all the way down till you reach the full width of the tool. And typically you don't want to do that because of tolerances and whatnot. That edge, the top edge, could be degraded. So typically you stay away from ball mills unless you absolutely need to. Now, the geometry types. In 2.5 axis machining, you can use any geometry type, lines, curves, 2D drawings. You can use wireframe drawings. Wireframe basically not used anymore much, but if you had to, you could use just the wireframe geometry. You don't have to have a part or 3D surfaces underneath that. And then obviously, if you do have a solid model, that's fine. If you have just an open surface model, that's fine. It doesn't have to be a solid. Basically, all you want here is to be able to grab lines, curves, or edges of surfaces to use as your control geometry. And
Well, one thing I wanted to add, Don, I mean, there's a lot of customers who are actually bringing in DXF files and using that for machining, especially for people who are doing cabinet type of work, and that's also quite very possible in our product. So even though you mentioned that wireframe is not used much, we do have a lot of customers using, nesting and DXF files. So there's a whole class of customers who are doing that. So
okay,
that's possible in our product too.
okay. And as Joe mentioned, you can bring in drawing files. DWG, DXFs are typically from AutoCAD source files from an AutoCAD system. You can also bring in IGES files and step files. And like I said, it can be a full solid model. As long as you can grab those edge curves and use as control geometry, you can apply 2.5 axis machining. One thing to note here that users tend to get a little confused on at first is that in 2.5 axis machining, the part really, the surface model really doesn't play any part in calculating the 2.5 axis toolpaths. Only the control geometry that you selected. From that geometry, you tell the toolpath how deep to go, how much to cut, how much stock to leave, what the step overs are, etc. You control all of that in your 2-axis operation. And the 3D model is really just there for visual purposes, so you can use the geometry that it provides you. I hope that's clear. Now, there's other types of control geometry other than just your...
Don, let me interrupt you. Sorry. That
Sure.
was a really good question, and I thought we should explain that a little bit more. One of the attendees is asking, do all the curves have to be closed? So I just wanted to make a comment on that.
Okay. Okay.
Uh,
Go ahead.
yeah, not necessarily. So we have a whole. You can think of control geometry as we could use both closed and open geometry. Any method that you're using for roughing, for area clearing, for instance, pocketing when facing, machining operations of that nature, where you're doing area clear and roughing type of operations, you would need closed geometry. But for anything finishing, for instance, profiling, slotting, and chamfering, filleting, and engraving, all of that, you can use both closed and open profiles or open curves as control geometry. So that's a good rule of thumb to have in your mind when you're selecting geometry. You cannot use open curves in pocketing or facing, but in any other method you can. Thanks, Don.
Okay, great. Also, there's other types of control geometry. You can use avoid regions as well as part drive regions. If you use avoid regions, basically, like it says, the toolpath will avoid those areas. Although, if you look at the part in the middle of the part at the top of the slide, where it points out the avoid regions, those regions have to completely bisect the control geometry region. So it can't be it can't overlap or coexist with the control geometry. You're defining an area, a closed area. It has to be closed, and it has to bisect the control geometry.
Don, the intersect is the better
Intersect.
word.
Okay, intersect. It can't overlap. It has to intersect. So think of it basically like that. And you can define those geometries, and I'll show you where those are in the demo. You define them on the Control Geometry tab of the operation dialog. Also, you can define fixtures. If you have clamps that you're wanting to avoid, you can define those in your machining job, and there's an icon, and I'll show you where that is, where you can define your fixture operations. One thing to note, if you want the tool to stay away from your void geometry, in other words, the tool, if you leave your stock at 0, the tool will go up to and stop at the control geometry. If you don't want that, then leave a stock value, and it will allow that much more material around your fixture and around your void region itself. So if anybody has any questions about control geometry, go ahead and submit those. But that's the basic explanation of what the different types of control geometry is in 2.5 axis. Now, in this slide here, we're showing you basically the contact point of the tool in different types of operations. If you look at the red dot, that's the cross section of the tool, not the tool holder, but just the cross section of the tool. And you'll see that starting from left to right and facing the center tip of the tool is where the tool path is laid. So the center of the tool goes to the outer extreme edge of the control geometry in facing, and it'll work its way in, step over until you clear the entire area. Pocketing is similar, but while the tool path is derived from the tip of the tool itself is contained to the geometry control geometry you selected for the pocket. So the outer diameter of the tool will go out to the control geometry and stop, and the tool path is defined at the tip of the tool. Similar for for profiling. In profiling, you can have a closed control geometry region or an open control geometry region. And just like in pocketing, the outer diameter of the tool will stop at the control geometry, and the tool path is defined at the tip of the tool. And also on the far right in engraving, you can think of engraving as if you want the tool tip to follow any curve. It can be a 2D curve, open curve, closed curve. It can be a 3-dimensional curve. It can be a contoured curve. The tip of that tool will follow that curve wherever it goes. And that, if you wrap your head around that, you'll think of a lot of ways that you can employ engraving other than just, engraving letters or part names and stuff like that. You can engrave anything, and that comes in handy if you want absolute control of the tip of the tool. Now here's just a 3-dimensional view of those different toolpath methods. Starting from left to right, you see a facing operation at the top of the block, and you need to know that in facing, the center tip of the tool is going to go to the outer perimeter of your control geometry. So the tip of the tool, the center of the tool will follow that outer perimeter. So you need to make sure that you have enough, clearance out there, that you're not going to hit anything else that you don't want to machine. Typically, this is used for the top facing areas, and not so much open faces, and I'll show you that in a minute. It works similar. So also in pocketing, the outer diameter of the tool will go out to the control geometry and stop, and the tool path is calculated at the center of the tool. Profiling, the same, but you're just putting one path at the outer perimeter of the tool, whichever side that you tell it to cut on. And again, the graving, the only thing that you're using in the engraving, if you notice there, is the curve itself. the part, the box, the slot that's being cut, that has no effect on your tool or the cut. What's driving the tool is the curve, and the tool tip of the tool is riding on that curve. Now let's talk about some other types of control geometry. You may have, if you're new to our plugins, you may have heard people talk about predefined regions. What they are is you can define your control geometry ahead of time without being in the 2.5 axis operation dialog. So there's a tab, I'm going to show you in the next slide, there's a tab in the machining browser where you can define predefined regions, and these, you can use them on a single part, or you can use them on a part that a pattern of parts like you see here, and we're going to show you how that works. Let's go to the next slide here and I'll show you a little bit more detail. So what you need to do is, all you need to do is define your first set of regions over here on the left. And if you look at the dialog, your regions tab in the top dialog here, you'll see that we created one region set for 4 different region types. Okay, so we have a region for the outer perimeter of the geometry. We have a region for the inner perimeter, and then a region for the one part of the letter and a region for the second part of the letter. So you only need to define that one time. If you have a part that has many of the same geometries, like an array or a circular array or rectangular array of geometry. And also in your first region, anything that you do to this region, you can define a bridge point, define the start point, but you only have to do that to your first region. And then there's a command here at the top right called cloning. Just select your region, pick the clone command, and it'll go find all of the same matching region types and add them to your set automatically. This becomes...
Yeah, it's actually does geometry matching. So
Yeah.
it's going to look in the part for similar or exactly similar geometry, but could be in a different location. So
Right.
it's a pretty important distinction there.
Yep.
And then for those of you wondering what the part is, those are actually planar surfaces. So if you look at the blue and the magenta area that are dark shaded, those are actually planar surfaces, and we have just created machining regions by picking the edges of those planar surface.
Yes, and
Thanks, Don.
those surfaces are not at the same level, so they can be deeper or higher, and you can control the cut levels in your operation dialog. Okay, so let's go talk about more about control geometry. You can control, obviously, which side of the curve that you're going to cut and where on the curve it's going to start cutting. One thing we need to note, that just some tips so you understand about the curves that you're going to be selecting. If you're doing pocketing, actually, if you're doing any type of machining with curves, it's always a good idea to first merge your curves into a single curve. What that does is it will alert you if your curves do not touch. In other words, if end to end, if they're not contacting each other, they will not be able to be merged into a single curve. And you will see that when you try to merge them, they just won't merge. So that's a good indicator that you need to go in and look at those endpoints of your curves, bring those together so they touch end to end, and then merge them into a single curve. Even if you're doing a profile with multiple curves, it's always a good idea to merge them into a single curve. It just makes it easier. Not only it validates the curves, but it also makes it easier when you're selecting them to drive your tool. Now, also, if you look in the top right illustration, this is how the start point and the direction of the curve is defined. So every curve when it's drawn, has a start point inherent in the geometry itself. And when you select that curve or surface edge or whatever as control geometry, the start point of that curve then becomes the start point of the tool when it starts cutting. So if you look at a curve, any given curve, if you stand at the start point and you're looking down the curve, the right and left hand rule apply. So if you want to cut on the right side, the tool is going to go to your right hand side of the curve if you're standing at the start point and looking along the curve. Again, left being left, right being right. And also it doesn't, this also applies to closed curves. All closed curves will have a start point and a direction, and you can define that right or left, cutting inside and outside of a closed curve region. Now let's talk about cut levels. This tends to be a complicated topic for new users trying to wrap their heads around, well, I'm only selecting a curve, how am I cutting in my depth? Basically, what you're doing is you're selecting your control geometry. If you look at the dialog on the right, this is typical for most all 2.5 axis operations. The first thing you want to define is where your cut geometry is located in relation to your cut. So if you look at the top right illustration, we selected the part geometry at the top of a pocket or the top of a curve, not at the top of a curve, but the top of your cut. And you define that by selecting at top. So you look at the top right illustration, you would select at top because your control geometry is at the top of your cut. If you look at the bottom right illustration, the control geometry you selected is at the bottom of your cut, and you would select at bottom. And if you move to the right, you can also, if you have the geometry at top, defined at top, either one really, you can divide those cut levels into a rough area and a finish area. So you got a rough depth and you got a finish depth. The rough depth and the finish depth values together will equal the total cut depth. So you have a rough and a finish. Then you can also divide the rough depth into levels. So how many levels do I want to cut for the full rough depth? So you see in this illustration here, we got 3 cut levels. So the total cut depth, if you look at the dialog, is 0.75. The rough depth per cut is 0.25. So if you divide 0.75 by 2.5, you get 3 cut levels. So you see 3 cut levels here. And the finish depth is also can be divided into multiple cut levels. Now in our dialog, we don't show a finish depth, but you can assign a finish depth, and then it will, the rough and the finish together will equal the total cut depth, and you can divide the finish cut into multiple levels as well. Now let's talk about the pick top. Let's say, for example, and this is a real world example where users have asked us, all I want to do is I want to level off my spoil board. I have my spoil board, it's got cuts in it, I want to cut it down to smooth it all out. Well, currently your spoil board may be at your 0, position of your machine. So you can define in your dialog, you can define a pick top for the top of the cut. Now the pick top doesn't have to be where your geometry is, where your control geometry is. It doesn't have to be where your stock is. It doesn't have to be related to anything. You're just defining a Z height and you're entering in the pick top field right here. So once you pick a point or define the Z height, that's where your cut depth is going to start from. So if you define your pick top and you give it a depth, and if that depth goes down past your spoil board, obviously, if that's what you're trying to do, then it'll clear out that much depth from your spoil board. And you can see here in this illustration, the control geometry is at the bottom of the stock. and the pick top is above the stock, and the depth of cut extends past the stock and past the cut geometry to the bottom cut here. So that's how you use pick top, and that's used in a lot of cases where you don't have a top or a bottom and you want to control the tool, obviously, so you can give it where the top is and a cut depth. I hope that's pretty understandable. If not, send us a question and we'll explain that a little bit more in detail. Okay, let's move along here because I want to get to the demo. Let's talk about entries and exits. Here on the screen, the dialog that you see on the right is the same for these types of 2.5 axis operations: basing, profiling, chamfering, filleting, hole profiling, T-slotting, remachining. You're basically controlling the entry and the exit. You have an approach, you have an engage motion, and then you have your cut motion. You can control each of those before you get to the cut start point, and they can be defined as lines and arcs along a path. You can give it a ramp. You can tell it a ramp height and it'll ramp down however you want that to go, or you can pick none. The same on the exit. You can define the retract motion and the length of the departure motion to get that tool away from your part geometry. And again, you can define that as lines and arcs or none. Again, here's another example for a pocketing. In pocketing, you can define the entry motion as a helix, a linear motion, or a path motion, which is basically a ramp. So in the dialog over here on the right, you see that we have a path set, and by path, that is a ramp. So it's going to start at a height and ramp down, and it's going to follow the contour of your toolpath itself. So here we're going to talk a little bit about stepped pocketing. By stepped pocketing, you can tell the pocketing operation that you have control geometry that you want to pocket, but you may also have a raised stepped area that you want to clear off as well, and you can do that in your 2.5 axis pocketing operation. And we have, if you want some additional tutorials, just go to your online help, and it shows you how to get to the resource guide and get some information and resources. And then, Joe, do you have something you were going to say?
Yeah, and also if you log into your portal, customer portal, you'll have access to the CamJam videos.
Yep.
And there's quite a few of those videos out there as well, so very useful. I mean,
Yep.
all of these webinars that we're doing eventually will make their way to the CamJam, so you can watch them again.
So, and also I want to point out we have two best practices guides for 2.5 axis and 3.5 axis machining, which goes over a lot of the things that we discussed and more. These are all best practices, tips and techniques in these two guides. So these are must reads.